Today, we are diving deep into the Solana Whitepaper. This is the document that proposed a completely new way to build a high-performance blockchain, and it made a claim so bold it pretty much forced everyone in the industry to pay attention. And yeah, this is that claim. 710,000 transactions per second. That's the theoretical peak speed the paper said was possible on just a standard 1 gigabit per second network. I mean, to put that in perspective, that number absolutely completely dwarfed what other major blockchains could even dream of at the time. Right, so that brings us to the main event, the central question of this whole explainer. How on earth is that possible? What was the secret sauce? What fundamental innovation did the Solana Whitepaper introduce that could unlock that kind of insane speed? Well, to figure that out, we have to look at the problem it was trying to solve. To really get the solution, you first have to get the problem. And it's not just about having faster computers or more bandwidth. The real bottleneck for pretty much every other blockchain comes down to something way more basic: agreeing on the order of events when nobody has a watch you can trust. Think about it. In a typical blockchain, all the different computers or nodes have their own local clocks. None of them are perfectly in sync. So to agree on the exact order of transactions, they have to constantly send messages back and forth. They're basically arguing about what time it is, over and over again. All that chatter, that consensus messaging, creates a massive traffic jam. Solana's approach? It's totally different. It says, forget arguing about what time it is. Let's build a single, verifiable clock directly into the blockchain itself. And this special clock, it has a name: proof of history. This is it. This is the core innovation, the big idea from the white paper. It's a brand new way of thinking about time in a decentralized network. A clock built not with gears and springs, but with pure cryptography. Okay, so here's the official definition from the paper. Proof of history is a sequence of computation that lets you cryptographically prove that time has passed between two events. So what does that actually mean? The key thing to get here is that it's not just slapping a timestamp on a transaction. It's a way of actually weaving the passage of time into the data itself. So how in the world do you build a clock out of math? It's actually really clever. You start with any random piece of data. You run it through a cryptographic hash function. Think SHA-256. Then you take the output of that hash, and here's the magic. You use it as the input for the very next hash. You just keep looping this process over and over and over again. Since you can't possibly predict the output of a hash, the only way to find out what the 1 millionth hash is to actually compute all 999,999 hashes that came before it. You've just created a sequential chain that proves work was done over a period of time. So this is how that chain of hashes becomes a history. To record something, like your transaction, you just mix its data into the sequence at a very specific point. Your transaction's data gets added to the previous hash before the next one is calculated. Now, what this does is permanently change every single hash that comes after it. It's like leaving a cryptographic fingerprint that proves exactly when your transaction happened relative to everything else. What you end up with is this incredible data structure, a ledger, where the passage of time is literally baked into the data. The order of events isn't up for debate. It's not based on some timestamp from a clock you can't trust. It's based on cryptographic proof. You can trust the order without having to trust any single person or node. Okay, so we have this amazing cryptographic clock. Fantastic. But how does that actually help the network process a crazy number of transactions? That's where proof of history meets the network's consensus mechanism. Here's how it works in a nutshell. At any given time, the network elects one node to be the leader. The leader's job is to grab all the incoming user transactions and use proof of history to sequence them, to weave them into that single ordered historical record. Then it processes them and broadcasts the results to everyone else. The other nodes, the verifiers, don't have to waste any time arguing about the order. They just take the history the leader created, quickly check the math to make sure the leader did the work correctly, and then vote to approve it. It's incredibly efficient. And that brings us all the way back to the beginning. Now that we understand proof of history and this whole leader verifier setup, we can finally answer the big question. This number. How does this architecture make this wild number even remotely possible? So here's the bottom line. Proof of history completely removes the single biggest bottleneck that slows other blockchains down, all that time and energy wasted just trying to agree on the order of events. Instead of this slow, messy debate for every single block, you have one leader who creates a single version of history that everyone else can verify almost instantly. By cutting out all that back and forth messaging, you free up a massive amount of network capacity for what really matters, processing transactions. And hey, don't just take my word for it. The white paper itself says it plainly. They analyzed this protocol on a standard network and showed that yes, this kind of throughput is possible, even with the hardware that was available back then. It's a direct result of this new architecture. So that kind of leaves us with one final, bigger thought. The Solana white paper wasn't just about making things faster, it was about changing the very nature of time in a decentralized world. So I'll leave you with this question to chew on. When a verifiable record of history becomes the clock itself, what else becomes possible?